Hello guys, welcome back once again. This is your Dr. Vantari Shiva from Seekers. Today we are going to discuss about moving charges and magnetism. Okay, right. Now in this video we are going to just cover the basic idea of magnetic field tentatively, and now in the next video we are going to talk about how do you calculate the magnetic field using Ampere's circuital law and Biot-Savart's law. Okay, so let us see what is magnetic field first. So you know that if you consider that there is a current carrying conductor, for example this is a current carrying conductor, now around which there is a magnetic field, understand? So the space around a current carrying conductor or around a magnet where the magnetic field magnetic effect can be felt, that is what is nothing but a magnetic field. Essentially this is nothing but a space. Essentially this is nothing but the space around current carrying conductor or the space around a magnet within which a magnetic effect can be felt. Now assume that how do you identify the direction of magnetic field? So I have told you that using Biot-Savart's law we can find out the magnetic field. Other one is Ampere's circuital law. Okay, we will discuss about that in the next video. Now if suppose there is a current carrying wire in which current I is passing up like this, what you have to do is you hold this current carrying wire in such a way that the thumb shows the direction of current. Okay, the curling of fingers will give you the magnetic field direction, isn't it? Let us say if suppose current is going like this, then you have to put your thumb downwards, then the magnetic field will be curling like this. Okay, and the beauty of this concept is if thumb is representing current, then curling of fingers represents a magnetic field, whereas the vice versa. For example, if you are taking a thumb for magnetic field, then curling of fingers will be representing current. You can actually use them invariably. Okay, yeah, going to next slide. Force on a moving charged particle in a magnetic field. Assume that magnetic field along x-axis. I am taking x, y and z-axis in this fashion. You know that the z-axis is like this. They are mutually perpendicular to each other, that you already know. Okay, now if suppose there is a magnetic field in this direction, I am assuming the magnetic field to be along x direction. Now I am throwing the particle somewhere in xz plane like this. So let me just represent this in this direction. The charged particle q is starting from origin. The charged particle q is starting from origin and moving in this plane now, which is making an angle theta with respect to x-axis. Now magnetic field is a vector quantity, velocity also is a vector quantity. Now if I take the velocity components, one component will be along x-axis, other one should be perpendicular to it. So I am taking this along z-axis now. So this will be nothing but v cos theta. I hope you know how to take the resolution, right? So if this is v cos theta, this will be v sin theta. Okay. Now the magnetic force experienced by this charged particle is found to be directly proportional to the charge magnitude, and also found to be directly proportional to the velocity which is perpendicular to this magnetic field. Here you can see this v cos theta is in the direction of magnetic field, and it has been found that the magnetic force is directly proportional to the perpendicular component of velocity, and that is v sin theta. I hope you are following, because here magnetic field is in this direction, v sin theta is in this direction. Both of them are perpendicular to each other. I hope you can see that. Right. Now it is also found to be directly proportional to the applied magnetic field for sure. Now if I just combine all of them, I get Fm is directly proportional to q v sin theta into b. If I remove this proportionality constant that has found to be 1, then I can write this magnetic force Fm is equal to q vb sin theta. So if you see this, the magnetic force acting on a charged particle moving in the magnetic field is directly proportional to charge. So for example, if q is equal to 0, that means the charged particle is neutral, or sorry, the particle is neutral. neutral in charge. That means for example, if you take a neutron or some particle which has a zero charge, neutral let us say, then essentially it will experience no charge even though it is moving in the magnetic field. Now if suppose, if you consider, if even though charge is there and magnetic field is there, but still let us say velocity is 0, that means the particle is at rest, then also the magnetic force will be 0. Next, if suppose even though the charge is there and it's moving also, if suppose magnetic field itself is 0, hence there will be no magnetic force at all. And also here the sin theta also will play a crucial role. For example, if I consider, if theta is either 0 or 180, what is the meaning of 0? That means if I take the magnetic field in this particular direction and velocity also in the same direction. What is theta, by the way? Theta is the angle between velocity vector and magnetic field, that you can see here, magnetic field and velocity vector. Okay, so if a charged particle is moving in the direction of magnetic field itself, then it will experience no force. Okay, because sin 0 is 0, so magnetic force will become 0. And other one is here, magnetic field is in this direction, and let us say the charged particle E is moving in this direction, or a negative charge is moving in the same direction like this. In either way, you can say that velocity is is parallel to minus of magnetic field. That means velocity and magnetic field are anti-parallel to each other. Hence, in this situation also sin 180 is also 0, hence magnetic force will be 0. So these are the 4 situations where the magnetic force can become 0. Going to next slide. Right. How do you find this magnetic force direction? So you have seen that the magnetic force Fm is QVB sin theta. What is theta? That is angle between velocity vector and magnetic field vector. Hence, can I write it as V bar plus B bar? Right. So this is the magnetic force in vector form. If you see this, how do you find the direction of the magnetic force? How do let us take some situation like this. For example, if there is a magnetic field in this direction and a charged particle is moving with velocity v by making an angle theta with respect to magnetic field. Now, how do you use this screw rule? So what you do is you take both the vectors, velocity and magnetic field vectors, and meet both these tails of the two vectors, and then at that location assume that this pen is a screw. Now let us say, now what you have to do is you have to rotate your screw, from first vector towards second vector. So I am keeping it here, I am rotating this in the direction of second vector from first vector like this. Now it is obvious that the screw will be rotating like this, that means it is going into the plane. So magnetic force at this location will be into the plane. Similarly, if I take velocity in this direction, magnetic field in this direction. Now what did I say? You have to take the screw and keep it the location where both these tails are meeting, and then rotate the screw from first vector to second vector, V to B. Rotate like this. Then the screw will be rotating like this. That means it will be coming out. Okay. Therefore, the magnetic force direction will be outwards. Okay. So that's how you can use the screw rule. And we also have other rule to find out this magnetic force. Let us see it again. So using Fleming's left hand rule, we can find out the magnetic force again. How do you do this? So you just take your left hand, and you have to take your thumb and these two fingers, middle finger and pointing finger, in such a way that they are perpendicular to each other. You can see that they are perpendicular to mutually each other and so on. Okay. So if you take it like this, and the thumb will be showing the force, indicating finger will be showing the magnetic field, and middle finger will be showing the current. So how do you take the current here? So essentially we are talking about the magnetic force Fm is equal to Q V cross B. Sir, you are talking about charge here and you are talking about current there. How does it connect? So if you see, if a charge is moving with velocity v, so for example, if a positive charge is moving in one direction, that means there is a current in the same direction. and if suppose there is a negative charge moving in this direction means with velocity v, let us say, then there is a current in the opposite direction to this motion, that you already know. That means what you have to do is you have to take the charge direction. If it is positive, take the direction as a current direction itself, and if a negative charge is moving in one direction, take the current direction in the opposite direction, and so on. Okay, so it is very simple to find out this magnetic force using this rule. For example, if you have got there is a magnetic field into the plane, and there is a charge moving in this direction, for example. Okay, that means what, current is in this direction now. Okay, and what you have to do is you have to take your left hand, and where is the magnetic field? Into FBI. Okay, magnetic field is into like this, and current is in this direction right now. So current is in this direction, so magnetic force that it experiences is upwards. So this is the direction of magnetic force. I hope it is clear. Next, let us take one more example. For example, there is a magnetic field out of the plane now. The magnetic field lines are coming like this now. For example, then if suppose the charged particle is moving in this direction, let us say, just for the sake of understanding, looking at it, and let's complicate the situation. I am taking this as a negative charge now, let us say, minus q is moving in this direction. That means what, there is a current in the opposite direction. Now you take your left hand again. Okay, take magnetic field first. Magnetic field is outwards, that means magnetic field is in this direction, and current is going in which direction right now? In this direction. What you do is you can rotate your fingers in this direction in such a way that middle finger shows the current. Then the magnetic force is shown by the thumb. Hence, the magnetic force will be downwards. Is that clear? Yes. That's how you will be finding out the magnetic force using Fleming's left hand rule. Going to next slide. We can also use the right hand palm rule for finding out the magnetic force. So here, you take your right hand, the palm shows the magnetic force, and this thumb shows the current direction, whereas the four fingers pointing will be in the direction of a magnetic field. Magnetic field. Now let us take an example and apply the same thing here. Let us say, for example, you have got there is a magnetic field in this direction. The magnetic field is in this direction, and if I take a charged particle moving in this direction, let us say. Now what did I say? You take your right hand, and point your four fingers in the direction of magnetic field, and the thumb shows the direction of current. So current, charge is moving in this direction means current also in the same direction. Hence magnetic field, current. So the palm shows the direction of magnetic force. So magnetic force here is into the plane. Okay. Now that means what, this charge will be experiencing force into the plane, then it will be pushed into the plane like this. Okay. Now let us say if I take the magnetic field into the plane like this, and there is a charge moving in this direction, let us say. Okay. So now again you take your right hand, show the four fingers in the direction of a magnetic field in this way, and in which direction the charge is moving? In this direction. Hence current is in the same direction. Okay. So this current will be in this direction. So rotate your thumb in the direction of current. Okay. Next, so the palm is showing downwards right now. Hence the magnetic force experienced by this will be downwards. This is how you will be applying the right hand palm rule. Okay. So let us talk about Lorentz force right now. So you know that if you consider there is an electric field, if you are keeping a charge q even at rest also, then the charge will be experiencing a force QE, that you already know. If it is a negative charge, it will experience a force in the opposite direction, but magnitude will be of the same. Now here that's equal to ma right now. If ma is equal to QE, and acceleration experienced by this charge is QE by m. That means what, the charge which is being kept at rest in an electric field will be accelerated. That means velocity will be increasing. Okay. If it is a negative charge, it will be experiencing deceleration and so on. Right. Now if you are keeping a charged particle in a magnetic field, okay, then it will experience a force. If you are just keeping a charge at rest, then it will not experience any force because V is equal to 0, so magnetic force will become 0. You know that Fm is equal to QVB sin theta or QV cross B. If suppose if I am throwing the charged particle with some velocity V, okay, then it will experience a magnetic force because the charge is there, velocity is there, and velocity and magnetic field are mutually perpendicular to each other. Hence, theta is equal to 90. If theta is equal to 90, sin 90 is 1. So it will experience a maximum magnetic force. Okay. Now, what if the charged particle is being thrown in electromagnetic field? For example, you have got electric field as well as a magnetic field. Then what happens? Then the charged particle being thrown into this electromagnetic field will experience both the forces, and that force is nothing but Lorentz force, and that is the net force. F is equal to QE. This is the electric force, and because of electric field, and it will also experience a QV cross B if it was moving into this magnetic field. So this force is nothing but a Lorentz force. Okay. So let us talk about a path of a charged particle which is moving in a magnetic field. For example, you have just seen that the magnetic force Fm is equal to QP B sin theta. Okay. So for example, if magnetic field and charge was moving in the same direction, then you have seen that the force was equal to 0. Okay. Now for example, if suppose a magnetic field is into the plane, and now you are throwing the charged particle in this direction with velocity V, let us say, then what happens? Slightly, if you use right hand palm rule, okay, then the current is actually going like this. Then magnetic field is into the plane. Magnetic field into the plane and current is going like this. Then this charged particle will be experiencing a force upwards. So hence it will slightly go up. The magnetic force will be upwards. Then it will slightly change its path towards this location right now. Now again the current was like this, now it has been changed like this. Then what happens? Force will be slightly moving upwards and so on. So because of that, what happens? The charged particle moving with velocity V will take a circular path here. Now the path of a charged particle in a magnetic field which is moving perpendicular to this magnetic field will be experiencing a circular path. Now what is that radius? Radius, so let us say the charged particle Q will be experiencing one force, that is QVB, magnetic force. Other one is centripetal force, that is mv square by r. So let us talk about that. What is this magnetic force? That is QVB, and I have taken the magnetic field and velocity mutually perpendicular to each other. So sin 90 is 1 QVB, and that's equal to mv square by r, radius. So this v that we gets cancelled. Let us say the radius of this circular path r is nothing but what is that? mv by qb. So can I say it as nothing but momentum by qb. Let us talk about the time period. Time period is nothing but how much time it has completed one complete cycle. Okay, so that is nothing but distance by speed. What is the distance here? It covers 2 pi r distance. When it is completing from here to here, it will cover 2 pi r distance. Okay. Now if you talk about the speed was v. Now let me just substitute this r here. That is 2 pi by v. R is nothing but m v by qb. This v and this v gets cancelled, and I get 2 pi m by qb is nothing but a time period for its complete motion or complete one cycle. Now what about frequency? Frequency is nothing but 1 by time period, and hence it will become volta completely. That is going to be qb by 2 pi m, right? And let us talk about angular frequency. Angular frequency omega, and that is going to be so that is 2 pi f, and that's going to be 2 pi qb by 2 pi m. 2 pi gets cancelled. I get QB upon m. Okay, that's your angular frequency and so on. And let us talk about in that r is equal to radius of the particle moving in this magnetic field is equal to mv by qb. Let us say sometimes they will be giving in terms of kinetic energy. Then this is nothing but momentum upon qb. So you know kinetic energy Ke is equal to half mv square. If I multiply with m and divide with m, I get m into v is nothing but momentum. So p square by 2m now. So what is momentum here? Momentum can be written as momentum square is equal to 2m Ke, and momentum is equal to root 2m Ke. If I substitute them here, then I get radius in terms of kinetic energy. Then it is going to be root 2m Ke upon qb. This is the radius expression in terms of kinetic energy. If suppose the charged particle is being accelerated through a potential v, then this kinetic energy will be equal to qv. Then what happens? I can substitute this in terms of Ke, I can substitute qv. So that is going to be root 2m qv upon qb. Okay, this q and that q gets cancelled. I get root of 2m accelerating potential v. This is not velocity, by the way, this is accelerating potential divided by qb square, right? Because I can write this as root q into root q. One q gets cancelled, then this b will become b square. That's what it is. Okay, so the remaining details of this chapter we will be discussing in the next videos. Thank you very much for watching. Thank you.